So in the last units, we talked about this representation of these musical spaces based on pitch and chords, and how this representation gives us a mapping of the space that we can navigate as composers to write a piece of music. So now we want to move away from this deterministic model, from this complete mapping of the space, and instead go and look at the way in which music emerges from these structures. And so here we introduce complexity through the composer as an agent that uses probability based on some aesthetic principles or a particular school or a particular genre, and by doing so it makes music emerge from the structures. Moreover, this concepts, this work can be generalized also not just as a means of composition, but also as a means of analysis, and how we can look at existing pieces of music through the lens of these complexity structures. Here I'm showing you a network representation of a chorale by Johann Sebastian Bach. Chorales by Bach are kind of a prototypical system of data that musicologists and computational musicologists use as like a primary example of this applications of models and theories in musical structures. So let's listen to it. So you saw how the composition kind of explores all these different spaces, the space of this network, in a very clear fashion. And here I want to point out that the way in which the different nodes are colored is not something that I decided in making the picture. The nodes are colored according to some specific algorithm that evaluates what is called the community structure of a network. You remember when we talked about networks that I showed you my social network, Facebook, that was where you could see the different groups of people belonging to a particular, say, category, like the musicians, the physicists, my Italian friends, and so on. And here what we are seeing is something similar, something that tells us that there are chords that are more connected to each other than others, that form regions that have a particular musical meaning. If you re-listen to this rendition of the chorale, you immediately realize that different colors correspond to different moods of the piece, the different keys, actually, of the piece that are used by Bach in this composition. And so we'll see how this becomes an important aspect of the way in which we can interpret and use this network representation of music for composition and analysis. So how do we build this network? How did I build this network chorale? Well, here we have a different score of a different composer. This is Ludwig van Beethoven. This is one of his late string quartets. And in this slide, I show you the procedure that I use to construct this network. So what I'm doing is I'm slicing the score in terms of chords. I look at the score vertically. You see these red rectangles. Each rectangle is a chord, and as such is represented as a vector. And each vector is a node of my network. The links now between the nodes, they are not the links that we saw before defined by the metric of the network space. Here there are links between chords that are one after the other. So if I go from one chord to the next, there is a link between these two chords. And these links are visited more than once because in the piece there are chord progressions that repeat themselves, and so there will be repetitions. And you see in the network on the right that some links are thicker than others. So that means there are some chord progressions or voice leadings, as we call it in music theory, that are more common than others. Now, if we look at these networks have very specific characteristics. They are characterized by nodes that have many connections, many links, so what we call hubs in network theory, that seem to attract the other nodes, so the more peripheral nodes that are less important, they have less links. This kind of property is called centricity, where there are nodes, or in this case chords, that are more central in the composition. There is the property of referentiality, in the sense that this structure of hubs and smaller nodes is actually repeated at different scales in the network. I mean, this is a very common property in many real networks. We need to always keep in mind that our musical networks are definitely way smaller than social networks or real networks that one can study also from the statistical point of view. So we are dealing with a number of data points that is not very large. But anyways, these properties exist also in this kind of networks. The network is directed, as I was saying before. There is a progression from one chord to the next, but not necessarily reversible. So it's more likely that you go from a chord to another than from this other chord back to the previous one. And so you have this kind of directedness property. And there is a hierarchy. So there is, as I was saying, linked to referentiality, there is a hierarchy that is a relationship between modularity classes, so community structure or chords that belong to the same regions, and the general structure of the network. This kind of structure has actually a name. These are what we call scale-free networks that are characterized by a distribution of the degrees of the nodes that follows a power law. And it's very common in many different real-world networks, and it's been studied extensively in the past 20 years, I would say. And there is a body of work that we can actually use in order to interpret and study the structure of these networks, also in the musical context. Now, the very interesting aspect of this discussion is that we talked about the topology of the network and its characteristics, but the characteristics that I just enunciated before are actually the same characteristics or kind of laws of what we call tonal harmony. That is the basis of Western classical music, for instance. So tonal harmony is governed by a few central chords. So the hubs are actually the important chords in your piece. The chords have a hierarchical structure. There are some chords that are hierarchically linked to other chords. The tonal harmony is asymmetric. There is definitely a tendency of moving from specific chords to other specific chords, but not vice versa. And this hierarchical structure is mirrored throughout the composition. So what we are seeing here is that by looking at the topology of our music network, the score network of a particular composition, we get, like, as an emergent property, the laws of tonal harmony, the ones that have been codified over centuries And of course, they are different depending on the different time period, the different genre, but there are all these kind of characteristics that become kind of a universal of tonal harmony. Now, there is another way of looking at the score that also is based on the same kind of procedure that I discussed earlier, but now, instead of looking at the network as kind of a static picture of the composition, what we want to look at is a time evolution of the piece. So how we relate the network structure with the actual evolution in time of the composition. And so for doing this, we can introduce what I call the score time series, where now each occurrence of a chord is mapped on a time representation, as you see in the right top corner of this slide, that now becomes the time series that I can analyze using typical or well-known techniques for analyzing time series. So if I do this, I can use, for instance, segmentation algorithms, so algorithms that identify segments of the time series that have some common behavior or common characteristics. And again, I'm not deciding anything here in this segmentation. Everything is decided by a statistical algorithm, mathematical algorithm that does this for us. And you see that this algorithm identifies various regions in the same string quartet that we were looking at, 10 of them in particular. And now we can combine the network representation and the time series to have a scored network for kind of the different regions or the different parts of the composition identified by the segmentation algorithm. So basically what we are looking at here, as you see in this slide, is a multi-layer network where each layer corresponds to a particular section of this time series. And we can look into these layers and identify specific characteristics of that layer that will have a musical meaning in the analysis of the piece. What we indeed see is that you combining network representation and time series analysis, we are able to identify the different tonal regions or different keys that Beethoven uses in this piece and their transitions. So if we look, for instance, at the layer 0 here, this is the beginning of the string quartet. The string quartet is in E flat major. And you see here that indeed the network corresponds to a structure of a E major section where the E major chord is the main chord of this particular area. And then the next one, 1, shares many chords in common with the previous one, but now is a transition to a G minor region, where the G minor chord that was kind of not particularly important earlier becomes the most important of that section. And so you can do this exercise layer by layer, and you associate different sections to different keys. And this is, again, something that comes completely from the topology and the behavior of the network as seen as a network of music. How do we use this in composition? In one of the next videos, I'll discuss how I use it in composition in a particular piece of mine that I will describe for you. But just to give you an idea, a hint of how this techniques, how this representation can be used in a compositional settings, I'm showing here a particular example, again, is a Bach chorale, where I'm looking at the way in which I can explore all the possible nodes and links of this network using a route optimization problem. So I have this network represented as a scored network, and I start from a particular chord, and then I start traveling through the network and basically building chord progressions. Now, if we analyze the original Bach progressions with the result of a route optimization problem, we indeed find that Bach was very economical. there is only a very small difference in number of steps and chords between the optimized route and Bach's route. Is just 117 steps versus 110. But it gives you an idea of how one could use this as a compositional process. So, for example, here I'm building a network using a probabilistic model. So I'm not using an existing score network here. I'm just building one computationally. And then I, with the same kind of topological characteristics that I'm observing in, say, a Bach chorale. So hubs, nodes are more important, less important, with the same kind of distribution, degree distribution and kind of links. I populate these nodes with a distribution of chords that can be actually the same distribution of chords that I observe in the actual Bach chorale. But now I have a different network, a different topology that I can use by applying a route optimization problem to extract a progression. And so I can use this as the basis of a composition. And in the next slide, you'll see how this can be done. There are two compositions. One is the original chorale by Bach, and the other one is actually a synthetic composition based on this approach of defining networks and populating the nodes with a particular chord distribution. Incidentally, these kind of networks that we're talking about were first studied by Laszlo Barabasi and Rega Albert, and they are called Barabasi-Albert network. And you see here their pictures next to the chorale.